You've never actually answered this question. Don't feel bad. Almost nobody has. You've felt fire your whole life. Held your hand near a flame, lit a stove, sat beside a campfire. You know it's hot. But if I ask you why it's hot, you'll probably say something like, because it's burning. And I'll tell you, that is not an answer. That is the question, wearing different clothes. I'm Paul Dirac, and I want to pull this apart with you, carefully, layer by layer, because the real answer involves electrons, quantum mechanics, molecular motion, and something about the fundamental direction of the universe that most people never connect to a simple flame. By the end of this, fire will look different to you, not less impressive, more. Let's start by destroying a comfortable assumption. Fire is not a thing. It took me a moment to really sit with that when I first approached the question properly. We talk about fire as if it's a substance, as if it's there, the way a rock is there or water is there. But fire has no mass. You can't bottle it, weigh it, hold a sample of it. Fire is an event. It's a process, a self-sustaining chemical reaction happening in real time, releasing energy as it goes, visible to you as light, felt by you as heat. The flame you see is not an object, it's a window into a reaction. So what's the reaction? When something burns, take wood or methane or the wax of a candle, you have molecules made mostly of carbon and hydrogen. Combustion is what happens when those molecules react with oxygen in the air. The carbon bonds break, the hydrogen bonds break, new bonds form, carbon dioxide, water vapor. And in that rearrangement, energy is released. But why? Why does rearranging atoms release energy? Here's where electrons enter the picture, and this is the real answer to why fire is hot. Every chemical bond has an energy associated with it. The bonds in your fuel, in the hydrocarbons, the carbon, hydrogen, and carbon-carbon bonds, are relatively high energy. The bonds in the products, carbon dioxide and water, are lower energy. When the reaction happens, electrons that were sitting in high energy bonding configurations end up in lower energy ones. They fall, in a sense, to a more stable arrangement. And that gap, that difference in energy, has to go somewhere. Energy doesn't disappear. The universe is firm on this point. It goes into motion. Specifically, into the violent, chaotic, rapid motion of the product molecules. They shoot away from the reaction site faster than they arrived. They collide with neighboring molecules and transfer that speed. The whole local environment becomes a frenzy of fast-moving particles. And that frenzy, that increased kinetic energy of molecules, is what temperature actually is. Here's the thing most people have never been told clearly. Heat is not a fluid. It's not a substance. It doesn't flow into your hand the way water flows into a glass. Temperature is the average kinetic energy of molecules, how fast they're vibrating, rotating, translating, colliding. When fire warms you, what's actually happening is that fast-moving hot gas molecules are colliding with the molecules at the surface of your skin, transferring their kinetic energy. Your nerve endings detect the increase in molecular agitation. Your brain reads the signal as heat. You are not touching something called hot. You are intercepting a cascade of molecular collisions, each one a tiny energy transfer, billions of them per second. That's what warmth is. That's all it is. Motion, passed from molecule to molecule until it reaches you. Now, why does the fire keep going? This is a subtler question than it looks. A single molecule reacting with oxygen doesn't sustain a flame. What sustains a flame is a chain reaction. The energy released by one set of reacting molecules heats the surrounding molecules enough to break their bonds and react, which releases more energy, which heats more molecules. The reaction feeds itself as long as fuel and oxygen are available. Remove the oxygen, smother it. Remove the fuel, starve it. Drop the temperature below ignition, quench it. Any of those three breaks the chain. This is why fire spreads. This is why it can grow from a spark to an inferno given the right conditions. It's not magic, and it's not simply burning. It's an autocatalytic reaction, a process that accelerates its own continuation. In a controlled sense, it's one of the most remarkable chemical phenomena on Earth, and humans figured out how to start and stop it tens of thousands of years ago, long before anyone understood a single thing about the molecular mechanics underneath. That's worth a pause. We mastered fire before we had any idea what fire was. Now look at the light. The glow of a flame is not decoration. It's a direct readout of quantum mechanics happening in real time. As molecules react and electrons shift between energy states, some of those transitions release energy not as molecular motion, but as photons, particles of light. The specific colors depend on the energy gaps involved, which depend on the temperature and the chemistry. Blue flames are hotter. The electrons involved are more energetic. The photons they emit carry more energy, and that pushes the emission toward the blue end of the spectrum. The orange and yellow you see in a candle or a wood fire, that's mostly not from electron transitions in molecules, that's from soot. Tiny particles of carbon, incompletely burned, heated to incandescence, glowing the way any hot solid glows, radiating light because they're hot enough to emit in the visible range. The flame is showing you two different quantum phenomena simultaneously: electronic emission from excited molecules and thermal radiation from hot solid particles. It's a physics lecture written in light, happening above your stove every morning. Here's where I want to be precise about something, the way I always try to be in physics. Combustion is extraordinarily well studied. We've been burning things for all of human history and studying the chemistry intensively for well over a century. And yet, a complete first principles description of a turbulent flame, from quantum mechanics up through all the intermediate reaction steps, accounting for every radical species, every collision, every photon emitted, that is still beyond what we can fully compute. A simple methane flame involves hundreds of distinct chemical intermediates and thousands of elementary reaction steps. We can engineer combustion beautifully. We can build engines and turbines and controlled industrial fires of extraordinary precision. But the full quantum mechanical picture of a turbulent flame remains an open computational problem. The thing that cooked your breakfast is still not completely understood. I find that clarifying, not discouraging, clarifying. It tells you something about the gap between engineering and understanding, between being able to use a phenomenon and being able to derive it from scratch. Now I want to tell you something that, once you hear it, you won't be able to unhear. What I've described, carbon oxidation, electrons falling to lower energy states, energy released as molecular motion, that sequence is not unique to fire. It happens inside you, right now, in every cell of your body. Cellular respiration, the process your mitochondria use to generate ATP, is chemically almost identical to combustion. You are oxidizing glucose. Carbon-hydrogen bonds are breaking. Electrons are falling from high energy to low energy configurations. Energy is being released. The difference, the only real difference, is the pace and the control. In fire, the reaction runs fast and loose, releasing energy as heat and light in a burst. In your cells, the same chemistry is broken into dozens of carefully managed enzymatic steps. The energy is captured incrementally, stored in ATP, and spent precisely where it's needed. Your body is a slow fire, a fire that regulates itself, a fire that maintains a temperature, responds to its environment, reproduces, thinks. You are combustion, managed, and fire is you, let go. The distinction between the two is not chemical. It's organizational. It's the difference between a controlled release and an uncontrolled one. Both are electron chemistry. Both are the same thermodynamic process. What separates a living cell from a burning log is not the physics, it's the architecture. I want you to sit with that for a moment, because I think it's one of the genuinely strange facts about being alive. But now, the deepest layer, the one most explanations stop short of. We've established how fire releases energy. Electrons fall from high energy to low energy states. Molecular motion increases, heat flows, chain reaction sustains. But here's the question that opens everything up. Why do electrons prefer lower energy states at all? Why is there a direction from high energy to low energy built into the behavior of matter? This is where fire connects to something much larger. The universe has a direction, not in space, in time. Things evolve from ordered, low-entropy states toward disordered, high-entropy states. This is the second law of thermodynamics, and it's the closest thing physics has to an arrow, a built-in asymmetry in how things change. Lower energy configurations for any given system correspond to states where energy is more widely distributed, more spread out, harder to concentrate again. Electrons fall to lower energy states for the same reason heat flows from hot to cold and not in reverse, because the lower energy state corresponds to more ways for the total energy of the universe to be arranged, more disorder, more entropy. Fire is hot because electrons fall. Electrons fall because matter trends toward lower energy. Matter trends toward lower energy because the universe moves toward higher entropy. And entropy increases because the universe has an arrow of time, a direction it insists on moving. You feel warmth from a fire because the cosmos is running downhill, and your skin is in the path of that flow. Every campfire, every candle, every star, they're all the same story. Electrons moving toward stability, energy spreading outward, the universe becoming slightly more disordered with every reaction. The light and heat aren't side effects, they're the point. They're entropy being generated, energy being distributed, the arrow of time being enforced at the molecular scale. And you, standing near the fire, absorbing the warmth, your own cells running the same chemistry in careful, slow motion. You are not separate from this process. You are part of it. You're a local pocket of order, maintained at the cost of exporting disorder, running on the same electron transitions that light the flame, sustained by the same thermodynamic logic that will eventually run you down. Fire is not alien. It's not dangerous because it's foreign to life. It's dangerous because it's too similar to life, the same chemistry, just uncontrolled. When fire burns you, it's not attacking you, it's doing to your molecules exactly what your own metabolism does, just faster and without your permission. That's the thing about physics. It doesn't distinguish between the fire that warms you and the fire that is you. It sees the same electrons, the same energy gaps, the same thermodynamic gradient. The difference is entirely in the organization. And somewhere in that gap between organized and unorganized matter, between the slow fire that thinks and the fast fire that doesn't, is one of the deepest unsolved questions in science. Why does organization exist at all? Why did matter arrange itself into things that can ask why fire is hot? I don't have an equation for that, not yet, but I find it remarkable that the question, that small, ordinary question a child asks, looking at a flame, leads here, to electrons and entropy and the direction of time and the nature of life. The flame hasn't changed, but if you followed this carefully, the way you're looking at it has.